Hey guys, it's your talkative Krishna here. I'm I'm here with another new video and with some new information. So what today we are going to learn? Well, we are going to learn about equivalent inductance in series and in parallel connections. So before that, you must know who I am, right? Well, I'm Sai Krishna. I'm a student currently pursuing a data science bachelor's degree at IIRE. So, what are the objectives of today's presentation? We are going to learn about that first. Well, that is, we will introduce ourselves to inductance because we need to understand what is an inductance first in order to learn about the equivalent inductance in series and parallel connections. Next, we will explore inductors which are connected in series and inductors which are connected in parallel. So, let's start with introduction, shall we? Yes. Introduction to inductance. Inductance is the tendency of an electrical conductor to oppose a change in the electric current flowing through it. L is used to represent the inductance and Henry is the SI unit of inductance. 1 Henry is defined as the amount of inductance required to produce an EMF of 1 volt in a conductor when the current change in the conductor is at the rate of 1 ampere per second. An electric current flowing through a conductor creates a magnetic field around it. The strength of the field depends upon the magnitude of the current. The generated magnetic field follows any change in the current, and from Faraday's laws of induction, we know that changing the magnetic field induces an electromotive force in the conductor that we all know. Yes. Considering this principle, inductance is defined as the ratio of induced voltage to the rate of change or current causing it. The electronic component designed to add inductance to a circuit is called as an inductor. So, inductance is not a component, it's just a principle where inductor is the physical component which applies to this principle. So, what are the factors which are involved with inductance? Let's understand them. Number of wires turns in the coil. That is one of the factors. Inductance is greater when number of turns of wire in the coil is greater. More coil of wires indicates a greater amount of magnetic field for a given amount of coil current. Coil area. Inductance is proportional to the coil area. Greater the coil area, the greater of inductance. Greater coil area represents less opposition to formation of magnetic field flux for a given amount of field force. So essentially there are two factors that we need to consider. One is number of wire turns in the coil and is coil area. Good one. Next we are moving on to types. Well, there are mainly two types of inductance. First is self-inductance and later is mutual inductance. By this slide, we are finished with introduction part of the inductance. So let's move on to inductors which are connected in series. When inductors are connected in series, the equivalent inductance of the combination will be the sum of all individual inductance. This is just like equivalent resistance of series connected resistors. Now, without considering mutual inductance, we can write the equivalent inductance of a series connected inductor as this: L equivalent is equal to L1 plus L2 plus so on to n. So how we derived these inductors connected in series? Let's understand them. Let's assume there are inductors L1, L2, L3, L4, L5 with V1, V2, so on to V5 voltages respectively. Now applying Kirchhoff voltage law, we get the total voltage drop V across a series combination of inductors to be equal to V. The voltage drop across an inductor of inductance L can be represented as L di by dt, when where I is the instantaneous current through the inductor. So is the combination connected in series. The current through of the conductor is the same. Say it is also I. So from the above KVL equation, we get V is equal to L1 di by dt, L2 di by dt, so on, which can be compressed to V is equal to V1 plus V2 plus so on to Vn. Now V can be written as L1 plus L2 plus L3. We are taking L common and we are making a summation of it. So essentially it becomes L equivalent of di by dt, where L equivalent is the equivalent inductance of the series combined inductors. Hence L equivalent is equal to this. Now inductors connected in series. So what is the problem over here? So no, not a problem, but generally a question. Let us assume there are three inductors: 10 milliampere, 40 milliampere, 50 milliampere are connected together in a series combination with no mutual inductance between them. Calculate the total inductance of the series combination. So L total would be just the sum of it, and we have got the sum to be 100 millihenry. It's as simple as that. One thing we need to understand over here is there is a concept of mutual inductance. Whenever we keep two inductors very close to each other, mutual inductance is prone to happen. In that case, there can be directions which must be important, because whenever mutual inductance is in play, solving the problems on inductance is not as easy as adding the inductors. We must know the direction in which the magnetic field is in. So for that you must understand this arrow. So here is this example. As per the dot convention provided in the figure below, the current is entering through the dotted terminal of one of the inductor, and the same current is leaving the dotted terminal of the inductor. In that case, polarity of mutually induced EMF differs from the self-induced EMF. The equivalent inductance of the combination will be minus 2m minus 2m. But if you see a previous picture, just a second. Yes, if you see this picture, these are in the same direction. If it is in the same direction, we would use plus 2m. That is the minor thing that we must understand over here. Let's do a problem on mutual inductance, shall we? Yes, sure. Two inductors of 10 milliampere respectively are connected together in a series combination so that their magnetic field aid each other, giving cumulative coupling. Their mutual inductance is given as 5 milliampere. Calculate the total inductance. So as they are contributing to each other, it would be L1 plus L2 plus 2m, and we got it as 30 milliampere. Now it's time for inductors which are connected in parallel. Whenever inductors are connected in parallel, the reciprocal of the equivalent inductance of the combination will be the sum of the individual inductance reciprocal. We will learn the effect of mutual induction on parallel inductors later in this article or video. Without considering the effect of mutual inductance, we can write it as 1 by L equivalent equal to 1 by L1 so on to 1 by Ln. This is just like the equivalent resistance of parallel connected resistor. We may have to consider the effect of mutual inductance in the same way if required. So the derivation of it, we will use a similar example, but now inductors are connected in parallel direction, and current E at each inductor is termed as I1, I2, I3, I4, so on to In. Now applying Kirchhoff current law, we get the total current I entering in the parallel combination of the inductors to be equal to this. The current through an inductor of inductance L can be represented as 1 by L integral V dt, where V is the instantaneous voltage across the inductor. All inductors of the combination are connected in parallel. Here the voltage across each of the inductors is the same, and say also it is V. So from the above ACL equation, what we get is this equation. See, The reciprocal of equivalent inductance of parallel connected inductors is simply an arithmetic sum of the reciprocal of individual inductors' inductance. So a problem based on inductors which are connected in parallel but with no complexity. Three inductors of 60, 120, 75 millihenries respectively are connected together in a parallel combination with no mutual inductance between them. So let's calculate their parallel combination in millihenries, and here we are, by applying the standard formula, we get this. Now let's consider the mutual induction part. So whenever mutual induction is in the play, we must understand the direction over here. So there is a general formula here, that is L equivalent is equal to L1 L2 minus M square by L1 plus L2 minus 2M. Now we will come to the effect of mutual inductance in parallel connected. Yes, it is. So let's see. So this is the difference over here. So whenever they are opposite to each other, we would use minus sign in the numerator part. Let's see a problem over here. Two inductors whose self-inductance is 75 and 55 respectively are connected together in a parallel aiding. Their mutual inductance is given as this. So as they are in aiding each other and they are connected in parallel, so both numerator and denominator would become minus, and we get this. So what is the summary? Summary is quite straightforward. Whenever they are connected in series, you should use this formula, and whenever they are connected in parallel, you should use the below formula. But we must be aware of the mutual inductance role in calculating the equivalent inductance connected in series and parallel connection. Well, guys, thank you for listening to this video. I hope this would be an informational one to you. Let's meet again with another video. Till then, have a good one. Sayonara.